vocab questions on 7.1 first. Going once. Going twice. Something like no vocab questions on 7.1. Okay. What?
Electrical resistivity.
So, dang, I'm dying. Have you guys seen in a big stadium how people do the wave? Mm-hmm. Excitement travels around the field and everybody's going. Yeah.
Like a minion.
Yeah. You should realize that electricity is not actually moving electrons. It's often drawn, electricity is often drawn as electrons traveling through a wire, but there's no actual, like, extra electrons. There's just excitement traveling between atoms. So when you get one atom excited, it starts to wiggle, and one of the electrons goes, pop! Shoulder dislocation. Yeah. This is how I used to dislocate my shoulder. On mine, if you went like that, it would come out. So, yours too? Probably, yeah, it's pretty bad. Okay, so that excitement means that the electron goes to a higher level, then it eventually cools down and returns to its previous level by passing its excitement to the next atom, which is destabilized.
You'll break Maddie if you do.
That felt pretty brittle. So it's destabilized, forcing it to promote its electron to another level. And then when it restabilizes and returns, energy is emitted, which excites a neighboring atom who promotes an electron to a higher level. And then when that electron returns. And so this is passing excitement.
That's what it is?
Relax, everybody. The same way that the wave is excitement moving through the stadium while everybody stays in their seats, unless they stand for a moment and then they go back to their seats.
So that's electricity.
Electricity is when excitement travels among atoms. Each atom gets a little excited and then passes the excitement to the next. Resistance is the fact that the excitement eventually wears out. If you do a wave forever, eventually people are like, I'm not excited anymore. Resistance is some of that energy is not passed from electron to electron to electron forever. Resistance is a wire's resistance to electricity going through it. As electricity travels through the wire, some of that energy is just dissipated as heat. That is resistance. Yeah?
Wait, you're saying it's caused by when electrons jump from electron shells?
I think so.
You think so? That would be a good answer.
With electricity, yes, resistance is the objection to doing that. So resistance is the natural resistance to electrical flow. What else? Other vocab?
7.1.
7.1 vocab? All right. Warm up today. What is efficiency? Anybody? Yes?
The energy not released as heat.
The energy not released as heat. I understand what you mean. Another way to say that would be utilized energy. Getting the most for less. Anybody else have another way to think of what efficiency is? What does it measure? Yes?
Energy produced compared to consumed.
Produced compared to consumed. Okay, what else? Another way to say that?
Output compared to input.
Yeah, output compared to input. Another way to say that? One way that I like to say it is how much useful work you get from your input of energy. So how much of the intended outcome you got for how much of the income. This is all the same thing. Check it out. Input to output. I have a classic example, but please look up and notice this. I don't want to mislead you. You realize this unit flirts with physics, but you know that I'm not very good at this. There are real, actual physics teachers at this school, and some of them even know what they're talking about. You could talk to them, and they'll correct me left and right, and I respect them, and they know better than me. So don't be misled by my errors. I'm shooting from the hip a little bit. But check this out. With a big asterisk, that's to remind you that I'm just estimating here. So here comes an estimate. Watch. 100% chemical potential in gasoline is put into my SUV. When that goes into the engine, spark plugs, fuel injection, air mix, pushing the pistons, turning the crankshaft. When we transform this chemical potential into this kinetic energy, that's about 30% efficient at best in the engine. And the remainder is all lost as heat to the air. That's why your car heats up. That's why you need the radiator and the cooling fan and all that stuff. Now, we're not done because the car's not moving yet. We just have the crankshaft spinning. I don't really understand this part because I'm not mechanically inclined either. But there's something about crankshaft and transmission and gearbox and drive train and wheels. So between that crankshaft and making the wheels spin, we lose another roughly 15% of that total potential. Again, that's just heat. In the transmission of kinetic energy here to kinetic energy there, we lose another 15% of our total potential that was in the gasoline. Again, just as heat. That's why the other parts of the car heat up. And finally, when those wheels want to spin, that's not perfectly efficiently translated to moving car because the rubber is flexible and the asphalt is flexible and they stick a little bit, so there's some friction, there's some wasted energy. And of course, pushing that SUV through the air creates friction with the air. So look at this shocking number. Of the 100% energy that was put into the car, only about 8% is translated to motion. And I'm off somewhere because my numbers don't add up. Only about 8% of that gasoline's potential makes your car move. The rest is heating up the asphalt, heating up the air, heating up the drivetrain, or heating up the engine block. This is what we mean by efficiency. Input, in this case, gasoline's chemical potential, and output, in this case, car moving down the road. Here's another example. And this is one that you should know. That's why I told you to write it down. This is a critical example that you have to know. Almost every last watt of electricity in the planet is produced like this. Check me out. This is a pretty cool demo. you can see I have a little plastic tube. In the middle, you see that little square thing? That's a magnet. There's my magnet. You see that I'm spinning it? It's on a nail in there. That little thing in the middle? That's a magnet. Around my bundle of plastic, I have some wire. Somebody just looped wire. And connected to that wire on both ends of the wire is this little light-emitting diode. A little LED light. Now watch me. You guys see that I'm making a little bit of blue light on that? I am making electricity. I am turning burrito into blue light. Via beautiful man, and also magnet plus copper plus light bulb.
Does that mean electromagnet?
What?
It's the thing where you you wrap a wire around a nail and connect it to a battery and make it it's like a really strong magnet.
Same idea.
No idea.
Yeah. Okay. Of all the electricity on the planet, 99.9 is produced by moving a wire relative to magnets or moving a magnet relative to wires. There's a lot of ways to move the wires or the magnet. Please look up. You can put that on a stick and blow on it, so the turbines will spin the magnet inside the wires and you get electricity. It's called a wind turbine.
Oh.
By the way, let me give you guys a news flash you may not have heard. This is a fan. If I take this plug and I connect it to a source of electricity, electricity will move through here into the wires, which will push the magnet away, which will spin the shaft and blow air at you. It's called a fan. I translate electricity to kinetic energy. Everybody know that? Now here's the news flash. You can also go the other way and just blow into my fan. And if you do that hard enough to spin the blades, that will spin the magnet relative to the wires, and this just became a wind turbine, and electricity will come out of the wire.
Oh, really?
Yeah. I mean, technically, they put a one-way valve in these, so no, not really. But if you cut out that little piece in here, then yeah. Yeah. You gotta let a man dream. Come on. My little dreams, dude. My little dreams. You guys like my news flash? Do you guys know that a fan is a turbine and a turbine is a fan?
They look like fans and fans look like turbines.
If you remove the one-way valve, you can just plug in all those turbines and they'll just cool off to Tehachapi or whatever.
Palm Springs.
Yeah, yeah. You could chill Palm Springs if you had a big nuclear power plant nearby. That's so great. I love that idea. Just turn all those things on. All the golfers go, oh no! It's like, okay, fly out.
So they really want said that.
I really want to do that, yeah. Do you guys know that Palm Springs uses enough water to provide all the water needs for something like 7,000 villages in India or something? Because of the golf courses. There's some math about how many city blocks you get out of each golf course, and Palm Springs has one of the highest concentrations of golf courses. Coincidentally, it's in the middle of the desert, so grass in the middle of the desert. There's a lot of water, so I hate golf because of that. Playing the dirt, not wasting all that water. Okay, back to me.
Grass is some.
There's many ways to spin that turbine to make the electricity. One way is to dump a waterfall on the turbine. And if you can't get your hands on a waterfall, you can build one. It's called a dam in a river. So you pile up a giant reservoir, and when you let the water out, it spins the turbine. Do you guys know that? Man-made waterfalls?
Hoover Dam.
Yeah, Hoover Dam is just a big-ass waterfall with a little hole in the bottom. But then you're spinning the magnets through the wires. big old magnets, big old wires make a lot of electricity. The most common way, though, not wind, not waterfalls, is to boil water. You can boil water with geothermal energy, like heat from the earth. You can boil water with burning petroleum, burning coal, burning natural gas. You could burn your mom. Anything that will make steam will spin a turbine. And coincidentally, a nuclear power plant is just a really dangerous, fancy way to boil water to make steam to spin a turbine. The nuclear power plant is this part. Now here comes another efficiency thing for you. Oh yeah, bro?
Well, where are the rods?
Yeah, so they're just another way to generate the heat. And by the way, there are various ways to transfer that heat, and you'll have to learn all that in a couple chapters, so you'll wait with bated breath. Now watch this. Of all the energy that you put into the average power plant, roughly 33% are wasted before you make electricity at all. And then when you put that electricity on the grid, another 50% is wasted before it reaches your house. So if your light bulb uses 10 watts, that's 30 watt equivalents of fuel that went into the power plant. Yeah. Yeah, that's right. So we're, of those, 30 watts, you look at your light bulb, it's using 10. 10 went into space at the power plant. 10 went into space from all those wires. And then when it gets to your house, that 10 will make about 70% heat in your bedroom, and about 3 to 30, depending on the light bulb, will go light in your bedroom.
And that dissipates, is that enough that concentrated heat to actually up the climate in that area?
Locally, yes. Globally, no. So it's one of the many things that contributes to heating in homes and in cities, yes. So, watch this. The electrical generation and transmission efficiency is roughly 30% because of the 33% loss in generation and the 50% loss in transmission. Have we had enough of our
Wait, what is the
units?
Doesn't the dam overflow? Before it was-
Could.
50% of what happens after thermal.
Right after.
So when that-
So of these two,
Okay, so
you use half to get one. Does that make sense? 3 minus the third gives you 2. 2 minus 50 gives you...
a third of all of it goes
Watch the math. A third of 30 gives you 2. A half of 2 gives you 1. So overall efficiency is 1 output for 3 input is 33%. What shirt do you have? Oh, you have the one with the babe on it. What shirt? Okay. Now I'd like to, anybody, you bored with this efficiency thing?
Yeah.
Had enough, right? Good. I can make it exciting and then you're just going to forget everything after the semester, so I'm just keeping it mellow. I'd like to review yesterday's warm-up. The first law of thermoefficiency, of thermodynamics, might be. The first law of thermodynamics. Anybody remember what that was from yesterday's warm-up? Neither created nor destroyed, it just forms. Now please look up. That's about the amount, right? See, I wrote it. And the second law is about quality. Anybody remember that one? Yeah, quality goes down. When you change forms, some quality is lost. Energy quality deteriorates. Everybody got that, right? So now look, there's 2 types of efficiency. There's first law efficiency, which is what we've been talking about, the amount of input to the amount of output. This is study goal number 11, and it gets 3 stars. first law of efficiency is about the amount, what we've been talking about for the last 20 minutes of boredom. And the second law efficiency is about the quality. You see, you don't want to use a high quality input for a low quality output. I'll give you a perfect example. Have you guys noticed what my thermostat is set to?
No.
That's right, it's set to no heat. It's set to off. If you guys don't mind being bathed in rat poop and dust, I can turn it on.
No, I don't mind.
It's cool, it's just that. See, when I crank that up, there's a burner turning on somewhere in the room just past the jewelry room. And as soon as it gets hot enough, the fans will kick on and this thing will start blowing out a whole bunch of rat poop and dust.
Yum.
Turn it on.
But that turns it off. That doesn't really want to go through the rat poop and dust. I was just threatening. You gotta keep the kids awake.
That should be a good punishment.
It would be good punishment. Back to me though. What happens in that furnace is natural gas goes through a little solenoid and comes out of this big old thingamabobber. Anybody ever looked at those big emitters at the bottom of the oven? When the oven comes on, there's like 1,000 little big flames coming out of a big pipe, all these little tiny blue flames. So in the furnace, it's like that, but times a zillion. So there's like a quadrillion little blue flames heating up a big copper flange, a lot of surface area. And then you blow a bunch of air through that copper metal thingy, and then that air the heat dissipates into the air, and then the ductwork gives you some hot air. House is warm, or room is warm. But let's think about that. The input quality is very high quality. You guys realize that natural gas is a high quality energy source? You can use natural gas to cook your eggs in the morning. You could use it to melt lead and make ammunition. You could use it to dispose of the bodies and get rid of the evidence. You could use natural gas to heat the jacuzzi. Jacuzzi. You could use natural gas to make a really hot flame and take a bunch of sand and make it into glass for my windows. That's a high quality fuel because it can do a lot of useful work. But instead, we just heat up some metal to heat up some air and get another 2 degrees of warmth into my room. That's a pretty low quality output. 2 degrees of warmth? We could all just do a couple jumping jacks and get 2 degrees of warmth into the space. Here's another option. The people who designed this ugly-ass building in the 1970s, they thought of this. I'll show you the evidence. You'll have to look out the window. I hope you can see me.
Please, walk him out.
You guys see that?
Is it a tube?
Yeah, where this roof extends. That's designed very carefully for this location, this city, this purpose. You see, you're in period number 3. So you can't quite tell that in periods 1 and 2, and especially in the winter, because the sun is so low, we get sunlight streaming into my room to provide heat when the room is cold. Or to create heat when my room is cold. Later in the day, by the time you're in period 3, the sun has risen over that roof line. So the eaves keep us shaded so that it doesn't get too hot during the day. In the summer, when the sun rises higher, we don't get very much of that. In the winter, when it rises lower, we get the most of that. Very carefully designed to use a low-quality energy source for a low-quality energy output. Does that make sense to everybody? If you're trying to heat this room in Antarctica, you pretty much got to use the gas because that's a high-quality work. That's a very difficult job, right? Heating up this room in Antarctica, that would require a lot of energy. So yeah, you got to use natural gas if we were in the South Pole. But because we're just in Santa Barbara, low quality input, low quality output, that is more second law efficient. You guys like my two types of efficiency? Amount and quality? You like my examples? Good, I don't like you. Okay. Oh, let's move on to number 13, which is that amazing diagram that I'll have to put on the internet, but you got to write down a bunch of notes from this. Don't say I didn't warn you, it's pretty heavy.
What number is it?
Number 13. Don't say I didn't warn you. There's a lot of info in this diagram. It's pretty dense. I have to do some fast and furious copying.
Do I have to draw that?
No.
We're copying that?
Yeah. Okay. Allow me to explain what you are looking at here. Wait, I'll wait until you're done with your conversations. We have sources of American energy. These are the inputs. We have one example of a transformation using fuels to make electricity. Now that it's transformed some of it, we have all the uses of energy in the United States, including that electricity. And finally, we have the output. How much is useful work and how much is lost energy. Do you guys see me almost break my screen right there? Okay. This is why the district should not give me fancy toys. I hope it's not on the internet. Okay. One very important observation that you'll have to note in your paper. Our country as a whole, for all energy sources and all energy uses, is 43% efficient. 55% is wasted, and you'll notice there's a couple missing. I think that those are exported, but I could be wrong.
Or the statistics?
No.
Okay.
When I warn you like 17 times that it's about to be important and you should take notes, and then I say the numbers, that's the part where you write it down. Now, what?
33% efficient and 55% wasted.
Something like that. I want to talk about what our sources of energy are, and you need to know these as well. You don't necessarily have to memorize the numbers, but I would certainly write them down because some of them might be seen again. Hydroelectric is 2.7% of our energy budget. Biomass is 2.8. Geothermal is 0.3. Wind, the fastest growing sector today, is 0.15. Solar is basically zero. According to this diagram, it is 0.006, which is basically zero. Nuclear is 8.1. Only 3 more to go. Coal is 22.9. Natural gas is 22.7. And petroleum is 40.1. If we want to look at those energy inputs, you'll notice a couple of patterns. First of all, 85% of America's energy is fossil fuel.
85?
Yeah. So of all the stuff we do in this country, 85% causes global warming, or at least climate change. Because 85% of all the energy in this country is based on carbon bonds that have been underground for millions of years. And we're putting them all in the atmosphere. 8% is nuclear, which is a complicated conversation in itself. If you consider hydroelectric renewable, because you guys realize you've clogged the river, then it goes to the ocean and it evaporates and it rains and condensate, precipitation, and then you can do it again, right? So it's kind of renewable. You guys know the whole water thing? So if you consider hydroelectric renewable, you could say that about 6% of America's America's energy is renewable, about 6%. But you ask salmon fishermen and farmers and many Native American groups if they consider hydroelectric renewable, and they will tell you, no, not so much because it's killing my river. And so if we don't count hydroelectric as renewable, which Jose does not, because Jose likes wild rivers. If we're just talking about the truly renewable stuff, we're down to about 3% of our budget is truly renewable. So notice you've got your renewable number including hydro and your renewable number excluding hydro. Next, look at the electricity thing. You might notice almost all of that coal, plus the nuclear energy, the wind energy, the solar energy, a little bit of natural gas, all that biomass, all that hydro, that's all spinning turbines. And remember, by the time that reaches the user, we've wasted 67% of it. So look at how much energy goes into electricity. That's 38 units of the American budget. And only 12.5 are actually electricity reaching the plug. While 25.5 are random lost heat in the atmosphere. Just so you know, if you wanted to find the targets for American conservation, which is a question in number 13, by the way, the single biggest target is electrical transmission. The power grid. The power grid, electrical transmission.
That's the biggest target.
For conservation. The second biggest target is probably making that electricity, the generation. You know, everybody always talks about like compact fluorescents and sealing the door and stuff, but please look at the residential, commercial, and industrial users of electricity. I'll show you. You can just see it from the back of the room. If you can't read the numbers, you should still be looking. Unless you're busy using your cell phone, in which case, Julia, you're cool. You see this residential, commercial, and industrial? Those are about 85% efficient. Of the energy that reaches your house, yes, you should stop wasting it. And yes, that is an easy thing to fix. But that's not a lot of gray line. Do you guys see what I mean? It's not a lot of lost, wasted energy. Look, residential, that's how much is lost versus how much is useful. Commercial, that's how much is lost versus how much is useful. You look at industrial, 24.3 goes in, 19.5 is useful. Only that little tiny sliver at the bottom is wasted. That's not so bad. But compare that with transportation. Light-duty vehicles, freight, and aircraft, that's a lot of wasted. Look at how much is gray, and look at how little is red coming out of our transportation users. More efficient vehicles and less movement of goods and people. You know, recreational flying might be good if that was more expensive, just saying, because it hurts our planet a lot. A lot of wasted energy, a lot of environmental harm. Big old cars that help you make up for your personal shortcomings. You can find other ways, I suppose, to feel better about yourself. You know, local economies, the whole thing about shipping strawberries from Ecuador just because I can. You know, that might not be the best call, just saying. I know you can, but, you know, doesn't mean you should. So if we're going to find our three biggest targets, I'd say number one is transmission of electricity, number two is generation of electricity, and number three has to be that transportation waste. Now there's one last point I'd like to make, and I'm saving it for last because this is a political issue, and some of you don't know politics and don't care about politics or refuse to be bothered by politics. You'd rather other idiots make decisions that affect your lives. So sure, you could bury your head in the sand. That's why I left this for last. But there's a really important political issue highlighted here. You see, I don't know how much y'all listen to debates and election talk and all that stuff, but there is a difference in how political parties talk about energy. Less and less difference lately, unfortunately. I hear sometimes people say, I don't want to do business with international providers of petroleum. I don't like supporting the government of Saudi Arabia, perhaps, or Venezuela, perhaps. I hear a lot of people talk about the international dependence on foreign oil. And some people don't like that. You can see that of our petroleum, we import 24 out of 40. More than half. Almost exactly 60% of our petroleum is imported. Only 40% comes from our own land. And so you may have heard people say, well, let's stop our relationship with these other parts of the world and drill, baby, drill. How many of you have heard this political topic? Perhaps. There's a bunch of reasons why that is confusing a really simple issue. Here's one reason. All liquid petroleum is a blend of different carbon chains. I'm sorry to speak chemistry. At the very bottom of any petroleum deposit, there's really thick, gunky stuff like asphalt and tar, C200 down to about C70. That's a long chain of carbon. Okay? At the very top of all deposits of petroleum is a little bit of gas, natural gas, C1, C2, C3, and C4. Those are methane, ethane, butane, and propane, the natural gases. At the very top, there's this clear, lightweight, oily stuff called naphtha, which is like C5 to C7. And forgive me if I'm fumbling the numbers. We have great chemistry teachers. You should talk to them. Somewhere in the middle, there's a sweet spot for making gasoline. C13, C15, C17, something like that. That's just a little tiny sliver in the middle there, just the sweet spot. That's what we make our gasoline out of. Now here's the problem. We import a lot of petroleum because we have a lot of cars, and our American petroleum is usually this stuff or this stuff. Very little American petroleum has significant amounts of this stuff. So if we drill, baby, drill, there are perfectly valid reasons to do that. For one thing, petroleum equals money. So it would help our economy. That's undeniable. But we would export that. That's not gasoline. That would not lower our dependence on foreign sources of petroleum. Because our American petroleum is not the sweet stuff for gasoline. It would help our economy, no doubt. Money out of the ground, turned into cash, we export what we take out of our ground. So we can buy the stuff that we have to import from the places that have the goods. Saudi Arabia, Kuwait, and Iraq. Here's the other thing, though. There's another way where we actually could stop our dependence on foreign petroleum, and it is a lot. We have existing efficiency solutions. I don't know about you, I'm not ready to give up my Tacoma. I love my truck. It is an extension of myself. I have certain shortcomings that I overcome with my four-wheel drive and 6 cylinders. But I gotta remind you that if we wanted to cut down on our energy use, look at how much energy we waste in transportation. Far more than we turn into vehicle motion. We could erase all those imports if we could just cut down on the gray leaking out of the transportation uses. If we restricted air travel, if we restricted long-distance movement of foods, if we came up with other solutions to long-distance commuting, if we had more public transit, more efficient vehicles, higher gasoline taxes so people don't keep putting those big old wheels under that big old suspension to hold up that big old truck, we could just say goodbye to all of those international relationships that we complain about. When people talk about drilling as a solution to the international thing, that is a false solution. I'm not saying there's no reason to drill. Obvious economic benefits. It's just not a solution to the international entanglements.
Yes. What year should we have started acting on global warming? It's too late now.
I mean, kinda, yeah. That's like, what year should I have started my diet? Well, for one thing, you could just start right now. For another thing, you've had bad habits all along. They were bad habits since before it became a problem. I have no answer to your question about when we start acting on global warming.
It's so broad.
It's just like the diet question. I mean, seriously, should you have gone on a diet January last year or December the year before that?
What started the dieting?
From the get-go? And by the way, it's never too late to make it a little better. You know, if you're on your deathbed, you can still diet today. The real, the big turn in the hockey stick was probably kicked off by actions that began in the 70s.
Is Santa Barbara part of it? Or what?
But technically, the bad habits probably started in the 20s and the 30s. And seriously, the straw that broke the camel's back all the way to the beginning was the use of coal in the beginning of the industrial age. It's just been all downhill from there, a snowball effect in terms of climate change from there. What else? Do you guys like my explanation of our energy budget?